talk about standard deviation, what a variance is. We'll calculate the standard deviation of a data set. We'll talk about what you use variance, and standard deviation for, and then we'll talk about the empirical rule. Okay. So when we start, we had these mini beach balls that we measured. You guys have your data sheets from Termaine? Okay. So if we look at our beach ball data, I'm going to write this down. All right, so if we look at our data, these were the diameters. Not diameters. I'm lying. It wasn't diameters. It was circumference. So we had those little mini beach balls, and these were the circumferences in inches. So 13.7 is my smallest. And if I make this my 13.7, we have one of those. Okay, and then I had 14. So I have 1, 2, 3, 4, 14s. And then 14.3. $14.5, $14.6, two 14.8s, 15, and two 16s. Okay, now if we look at this, it's not a perfect curve, but it's kind of in the general, I mean, this would actually come down faster, but it's not a perfect curve, but you can see that most of the data is in the center. Without the 16, it would be closer, yes. Now with these, the reason we don't have a perfect curve is because we have mass-produced beach balls that were then individually inflated. So if a machine inflated them and inflated them with the exact same amount of air each ball, we'd probably get closer to a normal curve. But because, you know, we're individually blowing them up ourselves, and then, you know, you blow it up and then you push the little thing in and maybe air came out, you know, so it's not as perfect. But we can see that it should have represented a normal curve. Most of our beach balls we had that high point in the center. You know, most of our data was in the center and less going to the outsides. Okay. In reality, no real-world data makes a perfect bell curve. Okay, a perfect bell curve, if we were doing the dots like I just did, we would have, say, 4 dots, and then 3 dots, and then 2 dots, and then 1 dot. And we'd go down like that, and it would make a perfect curve. In reality, we're not going to get that. We're not going to get a perfect curve. So we get data that comes close, and we use words such as approximate and assume. We say assume a normal curve, or approximately a normal curve, things like that. And that means that what we do is we take the real world data and we sort of shove it into being in a normal curve. Okay, so far good? Right. When we have a normal distribution that's assumed, the bell curve is symmetric. The tallest point is the mean. Okay, and again, the mean is the average of all the data. And to calculate the mean, we add it all up. And we divide it by the number of numbers we added. Okay, and that'll give us the blue line, the tallest point in our bell curve. Okay, our standard deviation is a measure of the spread of the data. And that's actually a measurement of the spread of the data away from the mean. Okay. Now, a bell curve is symmetric. That doesn't mean they're all going to be the same height and everything. You can have a symmetric bell curve that's very tall and has really short sides, or you can have one that's really flat, and you know. So that standard deviation is going to kind of describe the shape of the bell curve and how it's going to spread out away from that center part. Does it spread out really fast, like just boom, or does it go slow and it's gradual? Does that make sense? Okay. When we look at our beach balls, so if I go back to our beach balls, we can say that on average they're 14 and a half. We can say give or take half an inch because see we have some in here and some up to here for 14. So the typical measurement of the diameter is approximately 14.5 inches, give or take half an inch. I didn't give myself enough room, and that give or take a half an inch is telling us, you know, where most of the data falls. Is going to be 14 and a half, and then or 14 or 15 and somewhere in between there. That's the most of the data. When we look at, say for example, this example A, the typical measurement is approximately $500 in the bank. That's the average, that's typical. And then we look at the next set of data over, and we go down 50 or we go up 50. And we say give or take $50. And if we were to highlight that and color in this curve, and we look at the area under the curve, you can see that this section here is going to have more shaded in than either of those two sections on the outside, even if we put them together. Okay, so this is telling us the spread of the data, and we're saying the most of the data is in here. So far okay? Same thing. Typical measurement is approximately 64 minutes played, give or take. Yeah, so we'll subtract 6, add 6 minutes. We went to the next data. Yeah, there's 6 to get from here to here and 6 to get from there to here. I think the typical measurement is how many ounces? There's decimals in there. So 20 ounces, give or take 0.1 ounce. Now what we have, is there any way to determine the actual values for a give or take statement? Yes, and that's what we're going to talk about next. Can a give or take statement go beyond a single give or take, do you think? Okay, we've got an opinion of no, and we will talk about this some more later. And then can all of the actual values be represented on a bell curve, do you think? Probably not, because you could have the average catch-up bottle is between, according to this, 19.7 and 20.3 ounces. Or you could go to Sam's Club, right, and buy a gallon bottle of ketchup. Or if you're on like an airplane or something, they have those little teeny tiny glass bottles that have like a half an ounce or an ounce of ketchup in them. Have you seen those? They're the most adorable little glass bottles of ketchup ever. But so no, not all of the possible bottles of ketchup are going to show up on your standard bell curve. You're always going to have some data, yeah, that's not on there, either a specialty item, or if you're talking about people, like average heights or something, you have people that are just crazy tall or crazy short. They're not going to fit in a normal bell curve. So that's definitely a no for our actual values. Now the give or take, this is a description of the spread. It's telling us how far the data is, basically spreading away from that average. So give or take is the most basic form of a standard deviation. Yeah, standard deviation is a measurement of the spread of the data. And so by saying, oh, well, the average person is, let's say, 5.5 feet, give or take 6 inches. And that's probably pretty close. Most people probably fall between 5 feet and 6 feet. Obviously, you have people that are less than 5 feet and you have people that are more than 6 feet. But I would say the majority of the population is between 5 and 6 feet. So you'd say the average height is 5.5 feet, give or take 6 inches. And that give or take is the most basic way you can discuss standard deviation. Okay? Standard deviation is a value that can be calculated, and we will talk about calculating it in the next couple sections. But right now I'm going to give you guys the standard deviation. So we'll say that the mean number of calories consumed by an adult in a particular country is 3,200. That's the average calories consumed per day, with a standard deviation of 150 calories. Now we're going to determine the intervals for standard deviation. Okay, so here's what happens, is we will draw a curve. It does not have to be a perfect curve, but we're going to say this curve I just drew is perfect. It's really not, but we'll pretend it is. Okay? Down the center of the curve, at the tallest point, you put a line. This is your average, your mean. So in our case, that is 3,200. Now we want to find our values within one standard deviation of the mean. If we go back and look at this curve, these were our values within one standard deviation of the mean. They're going to be most of the data. How do we calculate that? Well, here we get a give or take 0.1 ounce. Here we're saying a standard deviation of 150 calories. That's saying give or take 150 calories. So to calculate those numbers, we take 3,200 plus 150 and 3,200 minus 150. So 3,350 and 3,050. Okay. Again, what we're subtracting is this right here. So our next two values, and we want them where most of the data is, so the fattest part of the curve, are going to be 3,350 and 3,050. Okay. And it says to highlight the area under the curve for each interval. So we highlight all that, or shade all that.
Okay, so the additional subtraction, that's only for the first part, or that's for all of them?
We're going to be doing that for all of them. It's $150 for each, $150, 150 calories for each standard deviation. So when we do one standard deviation, we add and subtract 150, just once. Now if we do two standard deviations, let's go back to blue. I'm going to draw another curve. Yeah, we're going to actually add 250s, which will be 300 right there. So yeah, 3,500. And if we take away 250s, we have 2,900. Okay, now I'm going to put my points in that I had before. My mean was at 3,200. My first standard deviation was at 3,350 and 3,050. Then my next one, I have 3,500 and 2,900. Now if you look on the curve, we're almost where it's touching the ground at that point. So I came out to, you know, where it's almost touching the ground. And again, we're going to shade under that. And as you can see, almost all of our data is going to be within 2 standard deviations of the mean. Most of our data is within 1, but when you go out to 2, you've got almost all of your data. And then if we have 3 standard deviations, we'll draw a curve again. Again, pretend it's perfect. That one's really not close, though. Whatever. Okay, pretend it's perfect. It's a perfect curve. It's beautiful. We love it. And we want to go out 3 standard deviations, so we're going to add 350. So we are going to add 450, which puts us at 3,650. And then we're going to take away 3 150s. So that puts us at 2,750. Yeah, no, this is basically, we're just introducing. So again, I'm going to put in the values that I already had. And this is the 2 standard deviations from the mean. And then the 3rd standard deviation from the mean is pretty much at the end of your bell curve. You might have a couple values that fall, oops, writing the wrong number on the wrong side. You might have a couple numbers that fall outside of 3 standard deviations away from the mean. So you'll see I did not write it at the very end of the line, but it's really close. It'll be very few data points that fall outside of 3 standard deviations from the mean. And when we talk about empirical rule, we'll cover that more. So at this point, 99% of our data is in that shaded area.